Welcome, everyone. I hope everyone's doing well. Thanks for joining us on this Friday morning, at least here in the East Coast of the United States. A little bit early for me. I like to sleep a little later, but this is the time that worked out best for all involved. As you know, today we're having a conversation with Nobel Laureate Frank Wilczek, who's made tremendously profound contributions to our understanding of physics in a variety of arenas. You know, some people make a contribution in just one area and they do something that catches the community of physicists, catches their attention, sets the world on fire, in this case wins a Nobel Prize, and then just dig deeper in that area. But that's not Frank Wilczek. Frank, a very broad thinker, is willing to take on a whole slew of different problems and has because of that, made great contributions right across the board. We're going to talk about a variety of things: particle physics, some cosmology, but also want to spend some time talking about his new book. We can actually bring the cover of that up for a teaser, if you will. His new book, it's called Fundamentals, 10 Keys to Reality. Just read it. It's a beautifully written new book. So we'll talk about some of the ideas that Frank puts forward in that. But before we get to that, let's start, as we always do, with some of your questions, a little bit of roundup on some of the important ideas that people are discussing, debating these days. Let me just see if there's anything in the chat that catches my attention. Oh, Tanzu asks, what do you think about the hierarchy problem? Hierarchy problem is actually relevant to what we'll be talking today in some sense with Frank. But the hierarchy problem is this fact that when you look at the various mass scales in particle physics, the masses of the fundamental constituents, and you compare that to the fundamental scale that emerges from the understanding of the strengths of forces, the strength of gravity, and the various constants of nature, there's a big spread in scales. You no doubt have heard of the Planck mass. Planck mass is a numerical number in the units of mass that naturally emerges by a particular combination of Planck's constant, the gravitational constant, speed of light. You put them together in the right configuration, and you get something with the units of a mass, and the particular amount of mass is about 10 to the 19 times the mass of the proton. 10 to the 19. That's huge, right? So the fundamental mass scale that seems to emerge from our description of the forces of nature and quantum mechanics, speed of light, gravity, and so forth, that number is 10 billion times larger than the scale of masses that we actually see in the particles in the world around us. So the question is, why is there such a broad spread of scales? And we've been trying to come to grips with that problem for a very long time. The idea of supersymmetry that some of you may have heard of, this idea that for every known particle, there's a partner particle whose quantum mechanical spin would be different in slightly technical language. That idea was partly introduced to deal with this hierarchy problem. The quality of those partner particles within the theoretical framework allows for a very natural explanation for why the particles would have such a low mass. It all comes down to a symmetry principle. Whenever a number is really small, a natural explanation is, well, it must be small because some kind of symmetry keeps it small. I mean, 0 is the most symmetric number we know. You multiply it by anything, you divide it by anything, it stays the same. Symmetry is a quality of a system that is unchanged under a whole variety of transformations, right? You take a sphere, you rotate it. If it's a nice silver sphere without anything printed on the surface, no matter what angle you look at that sphere, no matter how you twist it and turn it, the sphere looks the same. It is highly symmetric. Similarly, the number 0 is highly symmetric. As I said, you multiply, divide, doesn't change. So if you can find a symmetry that naturally yields 0 mass for the particles, then you say to yourself, well, maybe that's why they're so small, and maybe that symmetry is not exact. maybe that symmetry is almost but not quite an exact quality of the world, the environment. And that would allow the masses to be near zero, but not exactly zero. And this is this approach that supersymmetry gives us. So the problem, of course, is no one's found the supersymmetric particles. Large Hadron Collider, the hope was that it would find all sorts of other particles that we hadn't previously seen, partners of the electron called the supersymmetric electron or the selectron, partners of the quarks. We'll talk about quarks today with Frank, no doubt. That's where a lot of his profound contributions have been made. Squarks would be the supersymmetric partners of the quarks. Look, I don't name these things. Sounds a little silly, but this is a real mathematical theory. And look, a $10 billion machine was built in part to try to find these supersymmetric particles. And it's been disappointing that we haven't found these particles. Is it surprising? Well, we never knew the energy scale, the size of the machine, therefore necessary to conjure these new particles out of the void. You know, E equals mc squared. We'll talk about this also a little bit later. You can read that as m equals e over c squared, right? So mass can come from energy. So you have highly energetic particles colliding, and that energy can be transformed into mass, into new particles. And the hope was by slamming protons together at the Large Hadron Collider with sufficient energy, we'd be able to convert that energy into the mass of these never before seen particles. Didn't happen, or it hasn't happened. May still happen. Maybe you need a more powerful machine. Maybe their masses are larger than we can conjure out of the vacuum, out of the void. So the hierarchy problem and this idea of supersymmetry as a possible solution still up in the air, not as favored as it once was. I mean, when I was a graduate student, I don't know, it was almost a foregone conclusion that the world was going to be supersymmetric, that we would find these supersymmetric particles. Almost every paper that I've written, that's maybe a little exaggeration, but the vast majority of papers that I've written in one way or another have supersymmetry at their core. And some of the papers that I've written are using supersymmetry as a mathematical tool. And as a mathematical tool, it's unassailable, right? It's a piece of mathematics. It doesn't matter whether the world makes use of this supersymmetric quality. When you're doing mathematics, you don't have the constraints of nature breathing down your neck. You can just do mathematics. That's one of the beauties, but also one of the pitfalls of mathematics. I mean, the reason why I personally shifted my focus to physics when I was quite young, it felt to me that the problems of mathematics were just too artificial in a sense. I don't know if that's exactly the right word. They were too lenient. Maybe that's a better way of putting it. I'd like the idea of doing mathematics with the goal of aligning it with qualities of the physical world. But nevertheless, math on its own is enriching, fun, gratifying, and supersymmetry has had a powerful impact in our understanding of mathematics. But as a tool to understand the physical world, yeah, that is still somewhat up in the air. Someone else mentioned something in the questions here, which I caught my eye. I don't know. Sorry, I can't give your name. It's somewhere in the chat there. But asked about this thing called the Hubble tension. You guys heard of this? The Hubble tension? This is this state of affairs right now where our measurements of the expansion rate of space, the expansion of the universe, have become so precise that when we find discrepancies between distinct ways of measuring the expansion rate of space, we have to start to take those discrepancies really seriously and ask ourselves whether we are missing something. I mean, right, Big Bang, right? Space. I think we have a little visual on that. It's always nice to start the morning off with a bit of a cosmological explosion. So if we can bring up that animation on the screen. Yeah, so you know, the Big Bang, things start tightly compressed. There's rapid swelling. Yeah, it's just a artist rendition. But you see that everything expands outward. Space itself is swelling. And the question is, how fast is it swelling? And there are a number of ways that we can get at that answer. One way is very direct. You look at distant objects like supernovae explosions, and based upon the redshift of the light that they emit, right? The light that they emit travels across space. As space is swelling, it stretches the wavelength of the light. That's called redshifting. And the degree of redshifting is something that we can measure because we know the processes that are happening in that system. We know the light that we would receive from it if it was sitting right next to us. And when we look at the light we actually receive, it's not that light. It's stretched out versions of that light, but we can measure the amount of stretching. And the amount of stretching gives us insight into the rate at which space is expanding. So that's one way of measuring these things. Another way is you look at the cosmic microwave background radiation, this heat left over from the Big Bang, and by carefully measuring it, you can build up confidence in an inventory of the things that are filling space, the amount of matter, the amount of dark matter, energy, dark energy. And using those insights, you can then predict from those measurements the rate of spatial expansion. It turns out that those two approaches give different answers, not hugely different, but different enough that they are in tension, right? Edwin Hubble is the person who found through observations of distant galaxies that space is expanding. So the tension is called the Hubble tension. It's not like a literal tension. Sometimes we do talk about tension in physics, and we'll talk about tension later on. Tension between two quarks we'll talk about. We'll get to that. But this is more a metaphorical tension in that these two measurements don't seem to agree. So what's the answer? I don't know. Nobody does, really. There are interesting proposals that people put forward that maybe there's a kind of ingredient that was present in the early universe that gave the universe a kind of boost in its expansion relative to what we would have thought. And this ingredient, we don't see it today, the theory goes, because it may have decayed. It may have drifted back to emptiness over time. So a fairly significant rewriting of our thinking about the cosmological progression. But who knows? Others, the more conservative approaches, some will say, it's going to go away, this tension, these two measurements. These measurements are difficult. And over time, they have certainly bounced around. But others say, no, we've really gotten to a level of sophistication in our theoretical understanding, in our mathematical predictions, in our observations from a whole variety of different sources, ground-based telescopes, space-based telescopes, right? And some would say the level of sophistication and refinement in all of those ingredients are such that when there is a discrepancy in two approaches that are trying to get at the same number, the rate of spatial expansion, you've got to take it seriously. So people are taking it seriously, and we'll just have to see where that all goes as we head forward. All right, before I bring Frank Wilczek in about 10 minutes, I thought it'd be nice to just spend a little bit of time, 5-10 minutes, talking about what it is that he won the Nobel Prize for. No doubt we'll talk about this again. I think it's always kind of nice on these subtle ideas to see it twice, leisurely with me, maybe more rapidly with our illustrious guest. So Frank, I'll have to ask him, I think he was in his early 20s when he wrote a paper with David Gross, another Nobel Prize winning physicist. They shared the prize. I don't know if we have a copy of that paper we can bring up on the screen. It's a short paper. Many Nobel Prize winning papers are quite short. You don't have to write a big dissertation, a big tome to make an impact. So this is the first page, just a few pages. I don't know how many it is, maybe 3 or 4 pages in total. Yeah, they're coming up on the screen here. So a handful of pages. And what they did in this paper was to give a mathematical derivation that aligned with puzzling observations. What are the puzzling observations? It had to do with quarks. And the observations seem to suggest that when quarks are in the vicinity of one another, when they're very close, the strong nuclear force, that's what holds protons together, the strong nuclear force gets very weak when the particles are very near each other, and it goes stronger and stronger as you move them apart. Like, that's unusual, right? I mean, if you talk about the gravitational force is very, very strong when things are close, and it gets weak as you move them apart. Quite the opposite. And what they showed was that when you take certain quantum mechanical effects into account, it's as if the roiling, bubbly vacuum of space has the property that it kind of anti-screens the force, right? Normally, if you have bubbly things happening, they can intervene in the force between two objects and make the force between them weaker. But the bubbly stuff, it turns out, makes the force stronger. And there's some, the little formula, I think we do have the formula that they derived. I don't know if we have it exactly the form that's in their paper. It's the so-called beta function of the strong interactions. Yeah, we won't get into the gory details here, but that number alpha in there, that is a measure of the strength of the strong interaction. And the beautiful thing in this formula, what wins the Nobel Prize, it turns out, as we'll talk with Frank, that minus sign in that formula, N there is the size of the color group. You know, it's all technical stuff. NF is the number of flavors, the number of quark species, basically. But that minus sign is what establishes that as you move quarks closer and closer together, the force gets weaker and weaker. As you move them apart, it gets stronger and stronger. And this also gives an explanation of why one would never see a quark on its own. Why would you never see a quark on its own? I'll show you an animation in a minute, but the basic idea relies on Einstein's E equals mc squared, right? Remember, Einstein wrote his famous paper on special relativity in June of 1905. But then in September of 1905, you had an afterthought, an additional little paper that he knocks off. I think we have the September paper. Yeah, here it is. Again, just a few pages. And it's in this paper, if we go, I think, to the very last page, that we have the formula E equals mc squared. Now, Einstein didn't write it in the form E equals mc squared. In effect, he wrote it in the way that I mentioned before. He divided both sides by c squared and had m equals E over c squared. Now, he didn't even use c for the speed of light. He used capital V, a different notation. It all means the same stuff. He didn't use E for the energy. He uses L that we have over here. You see it, if a body releases the energy L, and there must be a reason for L. I don't know, maybe in German. I don't know. I don't know why he used L. But L over V squared is the same thing as E over C squared. So as you see in that line, mass is related to E over C squared. But the point is, forgetting about notation, that's sort of fun to see. There's the genesis of the most famous equation in the world, right? That's kind of fun. But the point is, energy and mass are interchangeable. So I'll show you an animation in just a second, but let me explain it in words first. If you have two quarks and you try to pull them apart, the energy of the strong connection between them from the strong nuclear force, it gets stronger and stronger, more and more tension, more and more energy in there. At some point, the energy in the strong connection between them can be transmuted into the production of mass, namely two other quarks, a quark and an antiquark. So the connection between them can snap, but when it snaps, you'll find two more quarks. You won't have pulled that quark into isolation. Let's show a little animation on that. I think we have a little visual here. So you have two quarks. That's the strong force holding them together. More and more tension between them. At some point, the energy and the tension is so strong that it will snap, creating a quark-antiquark pair. So you can't get the quark in isolation. Again, those can snap again, right? Every time you try to pull a quark by itself, you wind up failing, because as you try to pull them apart, the energy ultimately gets transmuted into the production of a new partner a new partner quark. This also explains another issue that no doubt I think we'll talk about when Frank is here, and I think he'll be here in just a moment, which is, when you talk about a proton, and people have asked this in various other chats that we've had in the past, if you go to a book and you look up the mass of the quarks that make up a proton, right, the up, the down quark, you look up their masses, if you add them together, basically 3 quarks inside of a proton, the answer you get is a tiny fraction of the mass of a proton itself. So what gives? Right? We normally think of, a proton made of 3 quarks, add up the masses of the quarks, you get the mass of the proton. But no, you get a tiny fraction of the mass of the proton. And again, the ideas that we're talking about give an explanation for that, because again, the gluons of the strong interaction that hold the quarks together, they have energy. And indeed, if we show an atom. Do we have one? Atom can you show up? Yeah, right. So here's an atom, right? You got the electron cloud around the nucleus. There's a proton. Inside the proton, there go the quarks, but the quarks are held together by these energetic tubes of glue, the gluons, and they're in a sea of roiling production of quarks, antiquarks, and gluons all over the place. And it's the energy and all the other stuff that via Einstein's M equals E over C squared contributes the M, the mass of the proton. So most of the mass of the proton is not the intrinsic mass of the quarks. Most of the mass is this other stuff. So these are the ideas that Frank has been so instrumental in developing and transforming our understanding of the world. I mean, look, there aren't that many physicists who actually transform our understanding of the world. Einstein was one of them, of course. Frank Wilczek is on that level. So with that, it's my great honor to bring Frank Wilczek into our conversation. I think he is here. I'm told he is here. As we bring him in, let me just note that Frank Wilczek is the Hermann Feshbach Professor of Physics at MIT. In 2004, he won the Nobel Prize for the discussions and discoveries that we will be talking about and I just made reference to. And as I mentioned, he has a new book, Fundamentals, 10 Keys to Reality. And we're going to get into that in our conversation today. And as you may no doubt know, I'm now riffing because I have no idea why Frank isn't up on the screen here. I don't see him. There he is. I thought I was going to have to just amp for another 20 minutes or something.
Well, I enjoyed watching you for a few minutes there.
Yeah. Great to see you, Frank. How's everything?
Good, very good. Insofar as it can be good with the world falling apart around us. But I'm actually optimistic about the future.
Yeah, where are you now? Are you
in Concord, Massachusetts?
Concord, Massachusetts. And have you been there for most of the pandemic?
I've been here since mid-March. Right.
Yeah, right. No,
only small excursions to take walks in the forest and historic sites around here.
Yeah, for sure. And I mean, what is your feeling about what's happening this is not a political talk show, but what's your take on what's happening right now?
Well, I guess my feeling is this too shall pass. And if you think cosmically in terms of scales of space and time and even of human history, I think there's every reason to be optimistic about the future.
Yeah,
there are dangers looming. Of course, there's the specter of climate change and nuclear war, and of course, one could have even worse pandemics. But the ability of our understanding of nature to give us control and in principle, the resources that are available to us, and the rise of our understanding of mind, I would say, both our own and the minds we create, all those things point to fantastic possibilities for a bright future.
Yeah, no, I'm deeply optimistic too. I would say though, and I wonder if you feel the same or not. I like many, I guess, never thought that our democracy was as fragile as it is. I mean, somehow, you know, in school, you're brought up to learn about the three branches and the checks and the balances. But in the end, it ultimately comes down to the integrity of the individual at some level, at some deep level. And
yes, there are complex systems have unexpected instabilities, I guess, is the general lesson that people learned in dealing with plasmas. And you can see it happening in history and systems failing in unexpected ways.
Yeah,
we can try to learn from it, and I think I hope we can learn from this experience. But there are some people of bad character and bad will, unfortunately, that have gotten influential, and somehow we have to work past that.
Yeah, you've certainly done, you know, a great job, a heroic job. Obviously, we'll talk about your science in just a moment, but you spent a lot of effort on reaching out to more general members of the public. You've written a number of wonderful books, and we're going to talk about this book here today, you know, which is a beautiful contribution. You've also written columns that I've enjoyed looking at over the years, and many people have. And so, do you feel that books that, like you write, I mean, I write books too, do they simply preach to the converted, or do you think that there's a real chance to reach out beyond?
I think there's a chance to reach out beyond. It's a challenge. And frankly, I think my previous books have sort of been getting more and more sophisticated in the way they reach out and presenting the science in ways that are more digestible. I've gotten a lot of feedback from friends. I've gotten questions, and found out what people have trouble with. Also, what people are really interested in, which is not necessarily the specific facts. It's they're not interested in physics 101, or they've taken courses and they've managed to forget it, and or sometimes with prejudice, so to speak. But what they're interested in is understanding the world and enriching their experience of the world, and they're very curious about what we've achieved and what we know, not so much for the detailed facts or the equations, but for the view of the world that it leads, and why we believe in it, and how it empowers us.
Yeah, well, absolutely. You know, and one of the wonderful things about your new book is, if I can just sort of show, it's not a thick book.
No, it's not thick.
No, it does not take forever to go through. I have to tell you, every time I write a book, I say to myself, this one's going to be a thin book.
Yes, and this is for me a new departure too, and it was necessary to censor myself, and a couple of times I started all over again. I had a very good editor, Christopher Richards, who kept me in line, so to speak, and this time I kept thinking of specific individuals I was writing for, which were the friends I mentioned, whose questions sort of stimulated this effort, and then also as I was writing this book, my grandson was born, and that made me think what could I write for him that he would really benefit from as he was growing up, and that made me think about myself as a teenager, when I was thinking about what I wanted to do and what kind of questions I was asking. So I wouldn't have wanted to read, or I wouldn't have benefited very. Let me put it different. There are plenty of places, especially nowadays, in Wikipedia and the web and of course books, where you can get technical information if you want it.
Yeah.
But what people need is an orientation, or I think what people can benefit from is an orientation, clarity about the absolutely basic fundamentals, and it's a wonderful story that I think we should be able to present and expand people's minds with.
Yeah, absolutely. So we'll get into that in just a moment, but you mentioned, thinking of yourself as a teenager, and
yes,
can we go back there just for a moment? It's always nice for the audience here to get some back.
Nice for me too.
Yeah. You grew up in New York, right? Am I mistaken?
Yes, yeah. in Queens, way in the northeast corner of northeast corner of Queens. Almost, I could walk 2 or 3 minutes and I would have been in Nassau County. So way in the corner.
Way over there, right?
Yeah.
So I guess that may explain, because one of my questions was, you know, I grew up in New York, and many people who grew up and went to school there went to Bronx Science, went to Stockton High School, but you went more local. Presumably, it was just too far to travel.
It was basically too far. It would have been more than an hour commute each way to Bronx High School of Science, for instance.
Right.
So that I talked about that with my parents, but it really wasn't a sensible thing to do, clearly. And the other side of the coin is that the school that I actually went to, Martin Van Buren High School, at that time was quite a good school, and also was a very large school. So there were classes at all different levels, and it suited me very well.
Yeah, presumably you stood out there. I mean, you would have stood out anywhere, but you know, were you an anomaly? Did the teachers not know what to do with this kid who kind of presumably?
Well, a little bit, but you know, they threw me ahead a couple of grades. So at that point, it was. There was a cohort of us who could meaningfully communicate and change and trade ideas, and they were definitely subjects in which I wasn't the best student. And so,
like what?
Languages. I'm not particularly good at languages. I'm terrible, truly terrible, or awful at drawing for some reason.
Yeah. Me too.
I want to come back to that someday and learn to do it properly, but it's not natural.
Right. No, you know, the pandemic, of course, is the time as many people start to think, well, this is the time I'm going to take up. Were you tempted to take up drawing and during these?
Yeah, I've taken up juggling.
Oh, you did?
And and I have gone back, to languages. I've always been ashamed that I don't know a foreign language. So since I now spend time in Sweden, I've decided to learn Swedish, and I've made some progress there. Yeah.
Yeah, I used to spend time in Sweden too. I didn't pick up the language at all. So, but with the juggling, how's that going?
It's well, I found a marvelous video by someone named Taylor Glenn, which is an introduction to juggling, and I thought the beginning of that, it's very charming. But the beginning was truly profound. She said that people think that juggling is a process of throwing things and catching things, but actually juggling is a process of dropping things. So yes, you have to, when you see someone doing it fluently, you're seeing the tip of a very large iceberg of practice.
Yeah, right. No doubt. It kind of reminds me of Kaluza. Do you know Kaluza learned to swim just by reading a book on swimming and then dove in, you know? So,
well, I did that too as an adult. I actually, you know, growing up in Queens, I had very few opportunities to meet the water, and really got kind of a phobia about swimming. But then as an adult, when we bought a place by the lake in New Hampshire as a summer place, it seemed a pity not to be able to swim in the lake. So I read about it and took it up and learned at I guess I was still 30 at the time. Yeah.
That is a true theoretical physicist.
Right.
You can do anything by just figuring it out and then just doing it.
Well,
and you survived. You survived.
There was definitely an element of experimental trial and error in it. But I love the expression that I got from a fortune cookie that I kind of made one of my mottos, which is the work will teach you how to do it.
The work will teach. Yeah, right. Through practice, you get it. Yeah, right.
Yeah, we do so many things subconsciously. I mean, consciousness is just a gloss on what's going on in our brain, really, and we do many things that we don't know how we do them. Starting with, well, organizing our visual perception, talking, understanding, standing up straight, walking, all these things. We don't know how we do them. And that's been proved by the halting progress of artificial intelligence on all those fronts. So it's
Right.
been, we don't know how.
We have an amazing storehouse of information that's buried in there somehow.
And it comes from interacting with the world.
Exactly. Yeah.
It really comes. So in a really profound way, we are not just individuals. We have agglomerated a lot of the world into ourselves.
We're the beneficiary of 100,000 generations of forebears who built up.
Right, and also a lot of feedback as we grow up.
Yeah, absolutely.
Sure. You watch babies doing experiments. They drop things and pick them up or have someone else pick them up over and over again.
Yeah, when my kids were young, I wanted to see. I wanted to see that moment where language took hold. And yes, I remember the first words, but somehow it just happens.
It happens. Yeah, and it doesn't happen in a microsecond, but it happens in steps that are usually surprisingly fast. Yeah.
Yeah. No, and my daughter, her first words were in response to my son, a little bit older, and her first words, "Alec hit me." So it was out of need, to communicate.
Yeah, that's really the work, teaching you how to do it. Right?
Yeah, totally. So you graduated high school young, if I right,
yeah, 15. I was 15 when I was just around my 16th birthday.
And you went from there to University of Chicago.
Yes.
Right. So I want to ask you a question about that. I had a graduate student who was 15. He went to Caltech at 12.
All right.
And it was really tough for him because, he had the intellectual firepower, but he didn't have the emotional maturity.
Right.
To do that. Did you? What's your view of rushing ahead so quickly as you did?
Well, I didn't do it as fast as he did. Evidently.
Yeah.
And I think I was basically pushing the envelope of what I would be comfortable recommending, because I'd had plenty of friends and maybe not quite a normal social life. I was clearly less mature than many of my classmates along various axes, but close enough that I did get socialized and learned how to deal with people in reasonable ways. And of course, I picked up more at college. But I never felt disconnected from my peers.
Right. I think that's the vital thing. If you can feel part of the social environment, then it can, as you say, through the work, you can learn, at an accelerated rate. And from there you went.
I should say also my parents, and particularly my mother, was, kind of a very social person and also kind of a saint in terms of how supportive she was and how caring she was.
Did she push you, or was she hands off?
No, my father pushed. My mother just support. Well, she pushed in a very gentle way. She didn't push, but if in some way I was failing or doing the wrong thing, she would just be less happy than usual. And I was very sensitive to that because I was there. So
the whole question of how hard to push your kids is such a subtle one, and so dependent on who the kid is, their DNA and
their
experiences.
So, and that worked very well. My mother's technique, and I don't think it was something she was calculating about, was that she was just so supportive in general and when something was wrong in her mind, she just became a little less supportive, and I felt that very acutely.
Yeah. Well, look, there is nothing like a mother, man. Nothing like a mother. So you went from Chicago to Princeton. Did you go directly to?
Yes,
to graduate school there. And David David Gross was your advisor.
It's a little richer story than that. So I graduated in 3 years from Chicago, so I was even more
advanced,
more out of shape, out of kilter. And I went to graduate school in mathematics at Princeton because I still didn't really know what I wanted to do. I wanted to keep my options open. I was pretty sure I didn't want to do pure mathematics, actually. So I got there under somewhat false pretenses. And I had, up to then, I had been learning what other people did, and I had become pretty good at that, you know, but it's a big, I found it a big step to go from learning what other people did to doing something different. It's a big, intimidating step. Also, the pace is much slower. You have to understand that not everything you try is going to work. And so my first 2 years at Princeton, it's a combination of that kind of change and also not knowing exactly what I wanted to do. It was kind of a crisis. I was a lost soul. But then, and I tried different things. I went to colloquia and all in biology, chemistry, and different, as well as there was nascent computer science growing up there. But I lucked into, I was very fortunate because the math building and physics are connected at Princeton. It was, and the math building is actually a big tower, so it's fine hall, I guess, to wander around. So I wandered into the physics room place often, and I got the sense that very exciting things were happening in physics that used some of the kinds of mathematics that I really liked, used analysis and group theory and symmetry. And I came upon this very charismatic young professor, David Gross, who was teaching quantum field theory. And we just hit it off very, very rapidly. And, you know, within a few months after our first encounter, we wrote those papers.
Wait, so did you have the physics back? In other words, were you a math major at Chicago?
Yeah, I was a math major at Chicago. So I did not have a conventional physics education at all. I picked up, you know, I was interested in physics and took quite a few courses, but it wasn't my major. I had read the Feynman lectures as they came out. Originally. Right. And I thought I understood them, but you know, in retrospect, I clearly did not understand them in an operational, profound way. But so I was vaguely aware of physics, but I did not have a proper education. And
I mean, did you take a course in quantum field theory?
Well, that's how I met David. I sat in on his class in quantum field theory. I thought I should learn because there were lectures by Ken Wilson about renormalization group. He was visiting Princeton, and I knew Sidney Coleman was going to be around. Anyway, there's a sense of excitement. So I was always interested in quantum field. I had treasured as before that as a student books by Hermann Weyl. And Einstein was a great hero of mine, even when I was a younger teenager. And so and as I mentioned, the Feynman books. So as an undergraduate, I also read Dirac's quantum mechanics book. And I really liked that because it was kind of a different approach to linear algebra.
Right.
And very clean. Very thin.
Again, was it less than 100 pages or something? I think it was the whole thing, right?
Well, it depends where you decide to stop, but yeah, the basic framework of quantum mechanics is spelled out in very succinctly, for sure.
Yeah.
You know, if you want to look at his views on quantum electrodynamics and so forth, then it's more. But So I was interested in physics, but I didn't have a proper education. Anyway, I decided this quantum field theory course was being offered, and that was a nice, clean subject that you didn't have to have a lot of background for. So I did that, and David was the teacher, so there was the professor, and that was really inspiring.
And so I guess in your interaction with him, did this idea naturally bubble up to calculate, as we call it, the beta function?
Well, it wasn't the first idea we discussed. We discussed many ideas.
Yeah.
For possible things. I remember at one point I was proposing to calculate neutrino scattering. This is the kind of thing that I was thinking. But I wanted to. I understood that the theory of the weak interactions was kind of breaking open. That the gauge theories were really promising in different ways, and the model wasn't clear that what the correct model was, or whether the possibilities along these lines had been exhausted. So I wanted to do that, and then David was very interested in renormalization group, and Wilson, of course, had given these lectures about renormalization groups. So then in our conversations, eventually we wandered over to the question of calculating how the short distance properties, the renormalization group would apply to the gauge theories, and that's and there were interesting formal questions because scaling is not manifestly gauge invariant, and that I thought that was a nice clean problem. And then it was just calculating. David had a much longer standing program of trying to show that quantum field theory could not describe the strong interaction. He was trying to show that no way, no how. But when we calculated in the non-abelian theories, we found that there was a way, and not only was there a way, but it was sufficiently unique as a guiding principle that it led to a unique candidate theory for the strong interaction, which is now called QCD. We got it, and we were able to figure out ways of testing it, and it was way ahead of the experiments at the time, but eventually they caught up. Yeah.
So we showed, actually, before you came on, we showed your paper with David. We can probably bring it up again. It's beautifully succinct, short, and the key equation, of course. Maybe not exactly in the form that you wrote it down. I think we can bring up.
That's the letter. Yeah, the letter is right.
That's right. So can we bring up the beta function equation? I just want to ask Frank one question about that. So here's one version of that, and the insight that the interaction between the quarks, gets weaker and weaker as we get closer together. It's all in that minus sign in that.
That's right.
So,
it's summarized in that minus sign. When we calculated it, it was literally that. We did a calculation. It was, at the time, it was a technically challenging calculation, and sort of broke new ground in technique. But it was not, how should I say, it was not a very conceptual calculation. We followed the rules that Feynman and Fedotov and Popov and some pioneers had laid down for how to do gauge theories, and this answer emerged, and to our credit, we knew what to do with it. but the conceptual understanding emerged over the next 2 or 3 years of why this happens in kind of more picturesque terms. But at first, it was just a calculation that gave a minus sign. David was very sure it was going to not be a minus sign. I was at least not ignorant enough not to have a prejudice.
But did that make you nervous that so much hinged? I mean, minus signs are things that we often get right, get wrong,
Yeah, I don't think I've. No, I wasn't. I mean, there were many ways of checking the calculation. I calculated in all kinds of gauges. I compared known results in QED, and so there were many. There was no question about the sign once everything settled down. The hard part of the calculation, sort of at the level of nitty gritty, was just making all these cross checks agree with each other, and once they did, the overall answer was clear. So I wasn't worried about that, but what I was worried about was, is this a meaningful result, and despite the questions about gauge invariance?
Yeah.
Is And of course, does it apply to the world when we wanted to have it strong? In a way, that didn't bother me so much at that point. I was interested in getting a thesis and doing something that would kind of establish me as a person that would have a job, and so I wasn't worried about the question of whether so much. I mean, it would, of course, I would be great if it described the world, no question. And I was already and immediately thinking about getting a Nobel Prize for it, because if it was correct, it was the theory of the strong interaction.
Yeah.
But I was less worried about the upside. I was less worried about Hunter. I was less worried about that. Was sort of gravy. That was fun to fantasize about. But clearly, there were issues. Nature would have something to say about it, and experimental physics would have something to say about it. It wasn't clear at all at first that testing the theory would be easy. We had logarithmic corrections to this or that, which were notoriously difficult to sort out. The experiments that we sort of used as our lever were very, very crude. We were, just the phenomena of scaling, which was the thing we were trying to explain, was kind of, pretty semi-quantitative. But we wanted to say that, oh yes, so it's actually scaling, but also slight deviations from scaling, and this was way beyond the evidence at the time.
And what was the reaction? I mean, when this result?
The reaction was mixed, I would say. There were a few people who immediately took it up and became very enthusiastic. The people at Harvard who were doing gauge theories for other reasons saw ways of that was very welcome to them to have a theory of the strong interaction that could be used. Ken Wilson, I think, was very enthusiastic from the very beginning. He had ideas about confinement, which we really didn't. We only saw that the problem was difficult. We didn't really have a concrete picture of how confinement would emerge. But people I thought of as sort of older and wiser, like T.D. Lee, for instance, said, well, people see approximate scaling in different circumstances in nuclear physics. It could mean this, it could mean that. And there were more or less plausible alternative explanations of the things that we were explaining. So it was mixed. But the most common reaction was no reaction at all, because people didn't understand what we were doing. Right.
It was too new at the time. Yeah, for sure. Right. And so, it's a funny thing in physics. When results are sufficiently novel, they can generate the response that you're noting. But over time, they become the ones that are right, become absorbed in such a deep way that it's almost like second nature. It becomes. It's like,
well, I actually talk about this in the book. As a young faculty member, Val Fitch was the chairman at Princeton, and he became quite a good friend, and he was, of course, the experimentalist who discovered time reversal symmetry violation, or CP violation, but it's really closely related. And I was talking with him, and I was telling him my bright ideas about matter, antimatter asymmetry, and how that might be developed cosmologically, and I think even about axions at that time, which was inspired by this T violation phenomena. And I was talking about T violation like it was history. Not thinking that he was the guy who discovered it. He remembered very well when it wasn't a part of reality, and it was a startling new revelation. And he said, he looked kind of wistful. I don't think he was hurt. He was amused. He was a very, very nice, sweet fellow, and very serene. He said, well, I guess yesterday's sensation is today's calibration.
Right.
And I've seen that with QCD. Originally, when we, for many years, maybe for 10 or 15 years after our breakthroughs, there were, after a couple of years, it became credible that this was maybe the theory of the strong interaction. Got a lot of theoretical support. But at international conferences, there would also always be major plenary talks about status of QCD, or status of the strong interaction, where people would talk about the evidence. Was it convincing? And it was slowly building and getting better and better. And that was one of the big highlights, or maybe the highlight of this kind of international conference for quite a few years. But now the same activity, in fact, much more sophisticated, the same kind of activity, measurements and calculations of strong interaction processes at high energies have become a very highly developed art. And now it's called calculating backgrounds, because people want to take it for granted. And the whole idea that this theory might be falsified in a big way is no longer really credible. So the focus of interest is using it as a way of establishing a baseline for looking for deviations, and those would be the interesting things.
Yeah, right. Yeah, it is funny how that works. I had a similar experience when I was a graduate student. I learned about the Higgs mechanism, and it was taught in such a way that I had no idea that the Higgs had never been found. Wrong perspective that this was a done deal, because everyone was treating it as if it was a done deal, and then of course it just becomes, as you say, ultimately the background within more novel phenomena, and you try to find. You mentioned axions in what we were just discussing. I wonder if we could turn to that for a moment. That's another. I mean, you named axions. You discovered this idea.
Yeah.
I saw in your book you even give a genesis of the name, which was you may want to mention. I had no idea that
it's a laundry detergent, right? Yeah. That I once, when I was shopping with my mother, I think it must have been when I was in college and home for a holiday or the summer, went shopping and saw this detergent on the shelf called Axion. And I said to myself, gosh, that really sounds like it ought to be a particle, that, it fits with pion or meson or baryon or ion or anion, cation, and all these. So it really, and it's also, it's a Greek root clearly, and it's nice and short. So it really catchy. So I said to, I really did say to myself, I say a lot of nonsense to myself, but I remember this, that if I had a chance to name a particle, I would try to name it axion, see if there's a way I could bring in axion. And years later, not that many years later, a little bit later, the opportunity arose, because there was this remarkable sort of qualitatively new kind of particle that clearly deserved its name, and its motivation, it deserved a name, and its motivation was a problem that has to do with the axial baryon number current. It's a little bit of a stretch, but close enough. And that was close enough to sell to a Physical Review Letters, which is very conservative about this. If I told them I was naming it after a laundry detergent, there's no way that the name would have been accepted. But I didn't tell anybody until afterwards.
Didn't Sidney Ullman try to submit a paper to Physical Review with the name of a particle called a spermion?
A spermion, right. That's what we now call tadpoles.
Yeah, right. And that didn't fly. They rejected.
That did not fly. They rejected that, right. And right. I think also, this was way before my time, but I think Murray Gell-Mann originally talked about curious particles, not strange particles.
Oh.
But that was not allowed.
Right.
Yeah. Thank goodness.
Yeah, right. Yeah, we have enough fanciful language already. So, but the axion now is still hypothetical.
It's still
a particle that has not been detected. But you have put forward the case, and many people, thousands of people, have written papers on the possibility that this puzzle of the dark matter might be resolved with the axion. Now, there was a time when it was a footnote in thinking about dark matter. I mean, it was kind of there. I mean, hopefully, I don't mean not in any denigrating way.
Not me, but you're right. You're absolutely right. Right. Footnote is being kind. It was kind of regarded as a nut cult. But
things have changed now, right?
Things have changed. No, now it's well, at least it's if it's a nut cult, it's kind of grown into a respectable religion or something. Like it has lots of adherents and is supported by funding agencies and serious experimental efforts all around the world to detect the thing. So it has a very well developed theory. It was, and to me, one of the most impressive things about it is that it was introduced to solve a theoretical problem in fundamental physics, having to do with the fact, this time reversal property, that the laws of physics look very, very nearly the same if you run them backwards in time. The fundamental laws, that is. But when we worked out what the consequences of this new particle would be when you ran it through Big Bang cosmology, we found that it gets produced in great abundance and has just the right properties to make the dark matter. And that case has become stronger and stronger over time, both in the way that the theoretical concepts around the axion have been battle tested for 40 plus years and survived every challenge with flying colors. It even emerges from string theory, for instance. There's their axe. The experimental limits on the axion. The axion has the theory has an undetermined parameter, so axions could have different properties depending on one parameter. It's very much like the Higgs particle, where you didn't know the mass, but once you knew the mass, you knew everything else. And the range of axion masses where it would not be dark matter have pretty much been excluded. So if you have axions at all, so if you're going to solve this problem at all, you need axions, and then if you have axions at all, you're going to get dark matter, and that's one thing that's happened. One big cluster of things that has happened. The other big cluster of things that has happened is that kind of the competition has not fared well.
Yeah,
that people originally thought maybe neutrinos, some kind of neutrinos would be the dark matter, but that's pretty well ruled out by now. There were ideas that so-called WIMPs associated with supersymmetry would be the dark matter, and that's been the subject of very heavy experimental efforts. But so far, both low energy supersymmetry and directly searching for the WIMPs have come up empty.
Let me ask you a question about that, though, because do you find is it just curious, just a coincidence? I could, and people have, say many of the same words about supersymmetry and supersymmetric dark matter. I mean, in supersymmetry, you're trying to solve a completely separate problem, not the dark matter problem. Right. You're trying to solve the hierarchy problem. And then within supersymmetry, these WIMP particles, they naturally are produced in the right abundance to be the dark matter. You don't have to find
more or less. Yeah, I wouldn't know.
Within an order of magnitude or so.
Yeah.
So is it why?
No, I have been an advocate for low energy supersymmetry. As you know, it's also the way couplings unify is improved.
Yeah,
you have low energy supersymmetry. That to me is really powerful quantitative evidence in that direction. But low energy supersymmetry is not really a theory in quite the same way as the axion theory is. It has many more than one parameter.
Yeah.
And there are certainly regions of parameter space where you can retain the good features, and yet the contribution to dark matter would be subdominant or super really subdominant. Not so it's a little bit, it has, I wouldn't be shocked or appalled if some version of supersymmetry and WIMPs turns out to be an important part of the picture. It really should be, but I at this point I'd be disappointed if axions weren't the dominant contributor to the dark matter.
Any sense of time frame when there'll be some experimental?
Well, I've been saying 5 or 10 years for quite a long time, but I do think we're getting more realistic about, and as you alluded to, the world is getting more serious about it. Many more experimental efforts are being mounted. I think really for the first time recently, one experiment, the ADMX experiment, has actually developed sufficient sensitivity that they would have detected the cosmological background of axions if they had masses within a certain narrow range. So it's only now that we are developing the technology that clearly is going to put the theory to the test.
Yeah.
And it's difficult to say how long it's going to take. I would be, well, it could happen any day, but that would require a lot of luck.
Right.
At least no existing experiment except for ADMX can do anything, and their progress is slow. They have to look at one mass at a time, and it's a slow process. But I'm working on some antenna designs with collaborators that
really?
I think might improve things, and there are lots of ideas. So I can't say for sure, but I wouldn't bet against the possibility of discovery on a timescale of, say, 5 or 10 years.
Right. So are you a tinkerer? I mean, do you build stuff when you
Yes.
talk about it? You do?
Yeah. Well, I don't build serious, how should I say? I don't build serious stuff, but I build models. I like to build models. I like toys. I always have liked toys, games of all kinds. Yeah, so I do.
Wow. What do you think about these ideas that people put forward that maybe the whole dark matter paradigm might be wrong, and we just need to really rethink our understanding of gravity itself?
Not much. I mean, it's one of these situations where it walks like a duck and waddles like a duck and quacks like a duck. It's probably a duck.
Right. Dark matter.
The dark matter. There are many ways of accessing this phenomenon, and they all fit quite snugly into the so-called dark matter paradigm. So it's on the scale of galaxies, on clusters of galaxies, going back to the microwave background radiation perturbations in the early universe. It all makes it consistent. The way they are distributed around galaxies, and they're clumped, but not as clumped as the regular matter. Yeah. It all fits together, and people who've done numerical simulations, like Carlos Frank, have had spectacular success based on starting with standard Big Bang parameters, many of which are pinned down experimentally, and running it forward and getting something that's at least a good caricature of our universe. Right. So people who want to develop alternatives have a lot to answer for, and the existing attempts are not impressive at all.
Yeah, right.
General relativity is hard to change.
Yeah, it is.
You can add to it, but it's hard to change.
Yeah, for sure.
It's a profound theory.
Yeah, and the amazing thing is, even the parts of general relativity that you can say Einstein himself was less than convinced about, gravitational waves. He was sort of on the fence.
Right. Black holes.
Black holes, totally on the fence. There was a paper, I think, in 1938 where he tried to prove that black holes couldn't form.
That's right. Exactly. He thought he really did. He was confused about the horizon being a singularity. And
Yep. So yeah, he really put forward something that, you know,
and of course he struggled with the cosmological term.
Cosmology is another big one.
He introduced it, but rejected it ultimately on a combination of empirical and aesthetic grounds.
Yeah.
I don't think he would have been terribly upset.
Well, actually,
it's not zero.
That is interesting. You may be aware of this, but you know, the famous story, of course, is the one that Gamow tells, where Einstein says, you know, it was the greatest blunder of my life, you know. But there is a talk of his that I saw a transcript where Einstein says it will be in the future.
Yeah.
Measurements will determine whether there is a cosmological constant. He didn't just sort of wipe it away the way the story seems to suggest. So I think he would be totally on board.
Yeah, I'm sure of it.
Right? Yeah, without a doubt. So let's turn to you know, this book. I never get my left or right correct with these cameras. There. All right. There it is, exactly.
Yeah.
This came out, I think, just a couple days ago, right?
2 days ago, yeah.
3 days ago.
No, 3 days ago. The 12th.
On the 12th. Great. And so, you know, we began to speak about it a little bit, but I want to go a little bit further now. I mean, your motivation here is clearly to give insight into a scientific mindset as opposed to the detailed forefront, this newfangled discovery that, you know, it's really about how do you see the world through the eyes of a scientist, and the beauty of that, and the way that viewpoint naturally engages with a very human viewpoint.
And so exactly. But I also in each chapter I let myself speculate a little bit at the end, because again, when I wrote this for my friends, as I say, I have some very specific people in mind. I don't want to embarrass them, but they all asked the same kind of questions about, you know, what does it all mean? What do you actually do? And what's coming next? So I talk about, I try to be clear about what we do understand, and that's a lot, but also convey and why we believe what we believe. And I think I can speak for we in this context, that we have a lot of overlap, but and that's a process, and it's historical, and I try to talk about how it might have been different, so these things shouldn't seem too obvious to you, and put it in the context of experiencing the world and anticipating what might happen in the future. But I'm very careful to speculate. To speculate. I do speculate, but to separate the speculations from the facts. And things that, and when in the case of facts, to give at least some indication of why they're facts, why we call them facts, right? Yeah.
And so, what is my writing process is I don't have long outlines. I just sort of dive in, but then I'm a revision. I revise. Is that a similar thing for you? Or?
Well, my wife tells me that all good writing is rewriting, and I do rewrite a lot. And it's particularly this book. The reason it became short was that I did a lot of surgery and amputation of a much more extended, detailed, kind of wandering text in retrospect. And so it's all high points. And but I do outline a lot, and you can see that this book is very structured. It's in 10 parts, and each part has subparts. And so some of the scaffolding is still visible, more or less.
Does the book look like the proposal?
Yes, and broadly. However, I would say as it developed, it became more culturally and philosophically connected, and less purely technical.
Right. No, you make
I brought in history of ideas, some poetry, some history in the sense of history of especially history of ideas in science, going back to the ancient Greeks and other philosophical traditions to talk about how people, it could have been different. right? These guys weren't dopes. These guys, and so putting yourself in the mindset of powerful minds who thought differently is really an expansion of mind. This, and it's closely related to a great theme to me of modern science, which is complementarity. That there are valid different ways of looking at things, that you should, to do justice to reality, you should be ready to take them all in.
Yeah, we're totally on the same perspective there. My own recent book, I had a similar idea expressed differently, that there are just many levels at which you can analyze reality. And the question you ask, what level is the right one? And that level has its own language, its own vocabulary, its own concepts. That's
right. And knowing what's going on 2 or 3 levels below might not be terribly relevant to
Right.
If you're in a jury on a legal case, it doesn't really help very much to know that the victim and the perpetrator are made out of quarks and gluons.
Right.
It doesn't help you very much.
I'm gonna tell you, though, a funny thing, though, I was in a jury in a criminal case, and in the closing remarks, the defense attorney looks to me and says, "And you don't have to be a quantum physicist." Defendant is right. And in the hallway, "Oh, I read your books," But and he was right. The defendant was not guilty in terms of the evidence he put forward. But anyway, but I want to ask you a question about that. So we're totally on the same page regarding that perspective. But there was a moment in reading your book where I wasn't sure we were completely on the same page. And I wonder if you wouldn't mind spending a moment talking about that. It was on the issue of free will. I think we do agree, but I think we probably say it slightly differently. So so you come to the argument that asking whether we are free in the context of a reductionist perspective is kind of the wrong question to ask. Free will is this human conception. It's up here at this level, the human level. Yeah. And there's other level of reality down there, the quarks, the gluons, the electrons, and so forth. And it's that other. So when it comes to certain things, that bifurcation makes a lot of sense to me. And we talk about love and guilty or not in a trial, or hate or grief or anxiety, those qualities, those sensations of human experience. It doesn't make a lot of sense to try to talk about them in the reductionist language. They're just, different.
Yeah. And free will is a very, very useful concept.
Very useful. But here's how I would say it, and tell me if you agree with this. So when we talk about the sensation, say, of love or hate or grief, that human sensation, I agree, needs to be thought of distinctly from the reductionist account. If we talk about the sensation of free will, then I would also agree it needs to be separated out. But I do find that there is value in thinking about at least a certain kind of free will, and it may be a matter of definition. When we think of free will as having control over the physical unfolding, then we start to use a language that's so similar to the physical unfolding down at the reductionist account that I do find it useful to ask the question that you say that we shouldn't ask. Now, is it because your definition of free will is more the sensation, the human sensation of free will? Is that where we use slightly different language?
Well, I think there is a phenomenon of free will. I mean, here it is. I can raise my hand or not. I don't know. Can I decide? You tell me what to do, and I'll do the opposite. Right. And free will is an essential concept in law. We give an insanity defense if we say that someone is not in control of their decisions, and so forth. Now, so it's a very useful concept in many contexts, and necessary to address certain kinds of questions. The great problem, I think, that a better way to state the problem that is usually discussed in terms of free will versus determinism, to me, a much better way, a phrasing of the problem is, does mind emerge from matter, and how?
Yeah.
And I absolutely do believe that mind emerges from matter.
Right.
And we've seen how metabolism emerges from matter, how heredity emerges from matter at a molecular level, and you could even go down further if you wanted to. We understand. We don't yet have that account for mind, clearly, but so far there are no showstoppers. Neurobiologists have not come into any phenomenon where they have had to invoke souls or something other than the same sort of thing that we discuss in our core theories or standard model. And it seems that there doesn't seem to be anything missing. And even more than that, we do we, meaning the scientific community, do very, very delicate, sensitive experiments where we have to make sure we control all kinds of things: stray magnetic fields, stray radio waves, people walking by, tremors of the earth, and so forth. But we've never had to make corrections for what the guy next door is thinking. Be careful not to think certain thoughts, or you'll mess up the experiment. So I think maybe that's what you're getting at. That
it's definitely a big part. Definitely a big part of it.
There's so I'm very sympathetic to the idea that we can get to a deep understanding of mind and lay a foundation for the phenomena we observe in terms of molecules and ultimately quarks and so forth. However, having done that, I still think we'll talk about free will.
And that's an example of the nested layers, the different languages that women use. It would be virtually impossible to excise the language and concepts surrounding free will from everyday human discourse.
Yeah.
But in my mind, I always say, okay, what I really mean is the sensation of that free will. But because mind emerges from matter is fully governed by these physical laws, my ability to intercede in those physical laws that's illusory.
It's really not that straightforward, I don't think, because there are phenomena of quantum uncertainty and chaos and just sheer numbers that make the idealization that we can just compute what's going to happen, and not to mention a human being or a brain is not a closed system, so the whole universe gets involved. And that's not just a metaphor. I mean, you see things, and that changes what you think. So I think there are questions about what the wave, in quantum mechanics, if you know the wave function, then the evolution is deterministic. But you don't know the wave function, even in principle, you don't know the wave function. So it's not clear. I mean, it is what it is. We'll discover as we work out what the facts are, and presuming it's true, how mind emerges from matter, it'll be much clearer how to talk about it.
Yeah.
But I don't think the kind of Laplacian crude determinism that it's just a matter of solving the equations, and if we were cleverer, we would be able to do that. I think that doesn't do justice to the situation. The calculations are so impractical. Yeah. But even more, it's not even clear that they make sense in principle, because it's just not an appropriate way to describe this.
Yeah, I mean, I would agree at the level of predictive capacity. I totally agree with the perspective that you lay out. For me, though, it's a question of what are the governing principles, and is there the ability of the human mind to intercede in the physical unfolding in a manner that somehow is distinct from core theory?
So we touched on exactly those 2 points, and I think we do agree on those. I don't think there's any evidence.
Yeah.
It's certainly worth investigating, and my God, it would be the greatest discovery of all. It would be the greatest discovery of all time, in my opinion, if you could show that there's influence of mind on matter that's separate from the influence of matter on matter.
Exactly.
And we have very sensitive instruments now, and that we will understand how mind emerges from matter at the same level as we understand how metabolism emerges from matter, how heredity emerges from matter, or for that matter, we're constructing minds. We're constructing new kinds of minds that are getting very powerful and getting, up to human and in some cases superhuman levels on some fronts. And so that'll give us examples of minds that emerge from matter.
Exactly.
But we'll also, I think, over the course of the next few centuries, maybe we'll make progress on the next few decades, but certainly in the next few centuries, we'll have a very rich understanding of how human minds emerge from matter. And if it works out the way I think it'll work out, that minds do emerge from matter, and there are no such effects, then I think we agree on those are kind of the observable correlates of this discussion. Now, whether you want to say that's the absence of free will, I'm not sure I'm willing to go with you there, because free will is a very useful concept, and I experience it. So it's something that we have to do justice to as part of understanding how mind emerges from matter.
Yeah, I mean, there's 2 points that I would make on that. So, yeah, I think we do pretty much fully agree. But the one point I was make is, I think there is an implication of these ideas for some of the concepts that you mentioned, for the judicial system, right? Mm-hmm. Because when I think in the manner of the absence of traditional free will, not sort of the everyday useful concept of it, it eliminates the knee-jerk reaction for retribution in certain circumstances. It adds a certain kind of empathy to circumstances. So punishment now becomes more just a teaching tool in order to shape behavior through the stimulus of punishment, as opposed to punishing for the sake of revenge. And I think that change of attitude, at least, it helped me get to that change of attitude through thinking in this way.
Well, I think that's wonderful. Even if it's not quite right, I think it's a wonderful byproduct. And I think I would reach similar conclusions by related, but just a little bit different routes. Yeah, But I do agree that internalizing this concept of complementarity, that different descriptions are appropriate, and by internalizing, I think one of the great lessons of our fundamental understanding is that the distinction between self and not self is somewhat superficial, and that we're all in this universe together. We're made out of the same sort of stuff, and expanding your circle of empathy very, very wide, and sort of internalizing the idea that there's also other forms of wisdom that say, put yourself in the other guy's shoes, or we're all God's children. I think that those lessons are not contradicted by fundamental understanding in the way you come to them by different paths.
Yeah, totally agree. Now, you mentioned the possibility of creating mind in a machine, in a computer, and it doesn't. I agree. I don't think there's any fundamental obstacle to that. I don't know how long it will take, and we begin to see already with systems like AlphaGo and machine folding or a deep mind. You have these systems that they can learn on their own. They just study the data. They study the patterns. So it does suggest, and you mentioned this in your book, it does suggest that at some point we may have these devices that can, in an hour or 15 minutes, rederive all of human understanding. And so what do you think about that? Is that the future that we're headed toward? And does it have any impact on, when you think about the work that you're doing, it changes our understanding, it changes the world. But when you say, and a machine will be able to do that in 30 seconds, in the 25th century, does that color anything that you do?
It is a lesson in humility, isn't it? No, I do. Well, let me get a prop here.
Sure. We're waiting for Frank to come back for a show and tell. Anybody just joined us?
This is Archaeopteryx. I keep Archaeopteryx on my desk as a constant reminder of this. That I read a book by Olaf Stapledon, one of the visionary geniuses of science, well, I've read several of his books, made a big impression on me, but one, I think maybe the first one that I read was called Odd John. It's about a superhuman intelligence. In this case, it was a mutant, but a similar idea that was just able to function at a different level. And the biography of Odd John is written by a normal human. And at one stage, Odd John is talking to the biographer and says, "You are the Archaeopteryx of the spirit." And I think we have to realize that we are able to comprehend the world remarkably well, astonishingly well, but we can certainly see that there are more powerful ways of more powerful information processing and absorbing and abstract, whatever, more powerful thinkers on the horizon, more powerful minds on the horizon. Yeah. And that's okay. I mean, it doesn't, we humans are already not the best at we still have athletic competitions, even though cars can move much faster and so forth. We still love birds, even though airplanes can move faster and higher and so forth and carry things. And even at a more practical level today, I wouldn't be able to work at the same level without my silicon friend here that helps me do calculations and picture things and just gather information that's stored on the internet and so forth. So I think we'll have a coevolution. The human mind will have a coevolution, and maybe the vanguard of thought will no longer be things encased in human skulls. But that's okay. They'll be better. They'll be better than us. Right. They'll be better.
Yeah, and certainly
if we do it right, and of course there are many ways things could go wrong. But I hope that there'll be a coevolution, a period of transition, and humans will continue to live and thrive and be enriched by this, but they won't be the vanguard of mind anymore.
And of course, it could be that we do evolve to a form where the flesh and blood version of ourselves is something part of the distant past, right? It could be that.
Oh yeah, right. We could. I mean, actually Ray Kurzweil, who's one of the visionaries of this kind of thing, came from the same high school as me.
Oh, is that true?
Yeah, just a couple of years before, I think. Yeah. Well, I didn't know him, and I still don't know him very well. But yeah, he something in the air.
Predicted 2020, if I remember, to be the singularity. And
yeah, I don't believe in the singularity. I think it's not. I think in the parlance of physics, it's going to be a crossover. It'll be a gradual.
Sure.
Which is fortunate because it's going to be very complicated to adjust to, and I think it's another case where the work will teach us how to do it. We'll interact with these things and have a chance to give them feedback on how they're doing and to build up relationships and maybe I think an important part of the future will be cyborgs. So human brains in even closer partnership with our computers than now. So I don't think anyone is smart enough to predict how this is going to work out in detail. Yeah. But experience will. I do have a lot. Well, not faith, but a hope that and expectation, I guess, guarded expectation that increased intelligence will also be associated with increased empathy and increased experience of the world.
Yep.
So it'll all be good. It's not, and we shouldn't be jealous that our ancestors will be longer lived and wiser and kinder than we are. We should
I mean, so a lot of this conversation is predicated, not completely, but partly under the assumption that the so-called hard problem of consciousness is one that isn't actually a problem, right? This idea that an inner world can emerge. So do you see an inner world merely as the byproduct of certain complex processes? Is that enough of an answer to you, or does it puzzle you at all?
It certainly needs to be worked out in much more detail, and I'm sure the details might turn out to be very surprising. But I think, if your standards of explanation are low enough, I think you can already see the outlines of how it might work, and some experimental support for the ideas that most of what's going on in our brains is subconscious. We already mentioned how we don't really know how we walk or how we certainly don't. Even people who've tried to study it very carefully haven't gotten very far. And visual processing, we know a lot of bits and pieces, but it's like the theory of the strong interaction before QCD. It's not really a functional theory. But where was I going with this? Sorry.
Whether we can come up.
Yes, but I think there are experimental indications that most of what we do is subconscious. However, there is a kind of necessity to organize it all. There's an executive function that needs to be in place for very plausible evolutionary reasons, just to make sense of it all and make sure all these units are working together. And that, if you think about it, that would have to be something like consciousness that says, and there are famous experiments, which I mention in the book, actually, where you can see that there's a separate process of a unit making decisions and then reporting it to consciousness. Right. And that's a separate process, separated in time and place from where it's actually done and where it's reported. So when you think you're willing something, you're actually just accepting the report of what your unconscious actually did. Right?
Yeah, there are a lot of the global workspace theory, Michael Graziano, the attention schema theory. I think these are
they're
ideas.
They're not just theories. There were experiments by Benjamin Libet, especially, was the pioneer. But by now there are hundreds of experiments along these lines of separating the decision-making process from conscious experience. They are not the same thing. And right.
No, absolutely. So a couple more things, if you have a couple minutes, I just wanted to get your feeling on. Physics, science more generally makes progress usually because there's some kind of tension, some kind of the parts don't fit together. And we have a bunch of those on the table at the moment. And I'm wondering what your thoughts are. And one is, and you and I once spoke about this a long time ago, and you didn't seem very interested to talk about it, so you may dismiss me again right here. But the quantum measurement problem. We have Schrodinger's equation. It allows us to calculate how the wave function, the probability wave, evolves in time. But to go from that to the definite world of actual outcomes is still problematic as far as the detailed mathematical description goes.
I think of that as part, but not necessarily the most salient part of this question of seeing myself in the equations. To see how within the equations of quantum mechanics you can construct sort of step by step, well, not just quantum mechanics, but the world as we actually know it. So QCD and quantum, at least in broad. You of course you'll have to make simplified models along the way and idealizations, but just in broad strokes, how you can construct something that we would recognize as our experience of the world. So we wouldn't be talking about doing experiments. We'd be talking about experiencing the world, and then to show that this description has the properties that we actually experience. So, that's somewhat of a scandal. Is that we have this marvelous, very successful description of the micro world, and there's no reason to think that we can't step by step ascend different levels of description and reach the macro world, and we do that very effectively at the level of designing engineering structures and semicomputers and so forth. But to get all the way from there to see how mind emerges from matter, and then to see how the world as we experience it emerges from that description of mind, that loop has definitely not been closed.
Yeah.
But I'm not sure that separately thinking about the so-called measurement problem is going to help very much.
Right. I mean, does that suggest that you are more in a many worlds like camp, that it will just be Schrodinger's equation and nothing else will be needed once this other level of analysis can be undertaken?
Yeah, I hope so. I hope so. Although there does seem to be a big gap somewhere in the axiomatic structure of quantum mechanics, at least as far as I've been able to see. Somewhere you have to introduce concepts of probability and interpretation. I have been very influenced by a book called The Consistent Quantum Theory by Robert Griffiths.
Yeah, I know the book. Yeah.
I mean, not only is it very clarifying, but I think it's actually useful in making little models of quantum mechanical phenomena. I've been using it in my work, and there'll be some papers soon about this. But so those models are sufficient. The models that are described in that book are fully consistent with the principles of quantum mechanics and sort of recognizable descriptions of actual experimental situations. And I think, really as stripped down as they could possibly be, given those constraints. And you can't get away from this damn assumption of a probability interpretation. I don't see how. So I think that might have to be added to the Schrodinger equation.
Right. So going from the small to the big, there is some people claim there's tension, not everyone does, between, the inflationary cosmological perspective and some of the other ideas that even, Paul Steinhardt, one of the architects of the inflationary paradigm, has sort of shifted his view to a cyclic cosmology, one that repeats in time. What's your view?
Well, okay, I mean, Paul's objections, as far as I understand them, are basically phenomenological. He thinks the theory doesn't really fit quite.
But also the multiverse as a natural outcome, I think, is a thing that really turned him away from inflation.
Yeah. It doesn't bother me. It could be. It's kind of it's another lesson in humility, perhaps, for fundamental physics. That we might not be able to predict as much as we had hoped about the basic laws. We might have to leave some parameters as historical accidents or something. But I try to resist, because that's the easy way out. That's just a convenient excuse. If you're saying, "Oh, I failed, therefore it's a failure of principle." But it could be that way. It's certainly logically possible that some of the things we think of as fundamental constants are historically conditioned and are different elsewhere.
Yeah,
it's certainly very logical possibility. So we'll just have to see how.
Well, what if it's the case?
How theories develop.
Frank, on one point, let me ask you one question though. If it's the case that the breadth of the multiverse is so broad that any measurement would find a home in some multiverse. I mean, this is the issue that Paul said. Then he says, then we're in a realm that's just non-fundamental. Any measurement of the CMB,
that's just not true. I mean, we have our core theory, we have our standard model, and it's not a random. It makes many predictions, so it's highly overdetermined. It's not. So our description of the world is definitely not underdetermined. We have plenty. We have lots and lots of data. So and whether it takes, ideally we'd like to have a one parameter theory or zero parameter theory of everything, of the fundamental, or at least the fundamental laws and excuses for why the complex world we see around us is complex, and we shouldn't aspire to incorporate it in the fundamental laws in detail. But you know, whether in a way, whether we need to use one parameter, two parameters, or five parameters, or 20 parameters.
Yeah.
No, look, that's to me is a higher order question. But I think to say that we can't predict anything is ridiculous. I mean,
right.
We do a lot.
No, so obviously, I totally agree with you. But just to play devil's advocate, there is an assumption of simplicity in that, because you take the core theory, the standard model, there are a lot of zeros in there that we are assuming from simplicity. We don't even pay attention to those zeros, other fields, other couplings, you know. So if you allow,
but
there are principles.
We're trying. To me, the goal of science is to describe the world, and we're describing the world very, very well, and it's not underdetermined.
No, I make the same argument too. Of course, you know, what we do is, you know, we make our best understanding of the phenomena that we see, and then we modify it in the smallest possible way. When some anomaly comes along, we have to describe it as well.
And we use it. I mean, this is the basic procedure that was articulated by Newton and brilliantly exemplified by him, and that we've been following ever since, which is analysis and synthesis. You try to understand very basic principles by seeing them in the simplest possible way they operate, and then build back up by deduction.
Yeah,
and that's been spectacularly successful,
for sure.
And I don't see any reason to poo-poo it. Let's say that. How should I say it? It's not our job to describe all possible worlds, whatever that means. Our primary job is to describe our world, and the logical possibilities that aren't realized in our world. Well, that's curious, but it's not really the job, or to me at least, it's not really the job of fundamental science to explain that. No.
Black hole information problem.
Mm-hmm.
Another one of those arenas of tension.
Yeah.
Where do you think we are on that?
It's complicated, I guess. I think, you know, I was alluding previously to using these Griffiths type models. I've recently made progress not on understanding black holes, but on understanding lumps of coal. So how a pure quantum system can radiate, in that case, burn. You put in a highly excited state, it burns, the radiation looks thermal. And so, but we know, and it goes down to a ground state, the radiation, despite looking thermal, perhaps for a very long time, is actually not thermal. How can that be? Why? And I think I have a very clear understanding of that in the case of standard quantum mechanical systems. Now, black holes have additional constraints about how things are arranged in space-time and how you transmit information causally that, it's hard to resolve, and we don't have a lot of experimental data to go on. It's not clear that if we had a correct theory, we'd even know that it was correct. How could you know? I mean, but I guess it's a fun problem. It's not clear to me that it's a really central problem in describing the world.
Right.
And the inspiration I took from it was to try to understand not black holes, but things that have the sort of most basic things in common, that they radiate in ways that can look thermal for a long time and yet have to be pure states. How does that happen?
Right.
As far as I don't think there's any really deep mystery there, but to see it concretely was a challenge, and
it continues to be. Yeah. All right. So that was sort of the bulk of things that I wanted to talk about. One final thing, though, a lot of students watch these conversations that we've been having. Some young, some graduate students, some younger, and we've even had people write that their child, 5, 6 years old, sort of watches these conversations just to let the ideas wash over them. So to a young,
I recommend that, actually. I mean, it meant a lot to me. Well, I don't think, well, even at 5 or 6, I was a big admirer of Einstein, and I was immersed in the Cold War, and people were talking about advanced weapons, and it was pretty scary, of course, but the fact that people were controlling nature and could produce these spectacular effects, I was immersed in that. Of course, I didn't understand it, but just knowing that it's out there and this sense of excitement and possibility, and the space race, people going into space, and just to be exposed to it is great. And then you can fill in the details later. But an important part of filling in the details is you need patience, because it's unusual material, it's difficult. And to have that patience, it really helps to have the motivation and to see the goal.
Yeah. I was going to ask you if you had any words of wisdom for those students, but you basically answered my question before I even asked it. So definitely that is an inspiring outlook, that there is so much more to learn, and it's a beautiful.
So you should definitely cast a wide net. Don't insist on understanding. Don't insist on understanding everything before you understand anything. But at the same time, the complementary advice I would give is pay attention to the foundations. Do learn your calculus and so forth as soon as possible, and learn how to converse with a computer now, and just be curious and have fun. Find out what you love. And go there.
Absolutely. So everybody, this is Frank's new book. Let me try to center it in the frame there. Fundamentals, 10 Keys to Reality. Just came out 3 days ago. There's an even better image that you see on your screen right there. And, so, you should go get it. It's a beautifully written account that really allows you to see the world through the eyes of one of the great physicists of our age, and gives a different perspective on how we can engage with reality. So you should get it, read it, enjoy it, reread it. And Frank Wilczek, thank you so much for joining us today.
Thank you, Brian. Okay. Bye.
Talk soon. All right, everybody. That was our conversation with Frank Wilczek, Nobel Laureate for his work in quantum chromodynamics. And as you have seen, he's a very broad thinker who is concerned much more than the details, much more with how we human beings can relate to the world in a way that's exciting, creative, can even involve contradictory perspectives. But that's the beauty of having a human brain, the ability to engage with the world in a fundamentally human manner. So before we wrap up, let me see if there are any particular questions that you guys have in the chat. I'm looking over at it here, and let's see. So Elsa notes, never forget when you were looking in the sky, you were looking in the past. Elsa, that's true, both scientifically, and it's a very poetic idea. I like to think that everything that happens on planet Earth, right? The reflected light rays from planet Earth, they race across the universe and carry our present out to the cosmos. It's a kind of immortality in a way. The fact that something happens in the universe gives off light, and the light from that event has an imprint of that event, and that imprint just travels until obviously it reaches some destination. If not, it just can travel through the cosmos indefinitely, which is kind of an exciting way of thinking about how the world is. Susan Roy asks, when you use the word information, what precisely do you mean? It's not an easy question to answer, Susan. It's a vital question to ask. To some extent, when we talk about information, we're talking about the data necessary to specify a physical system. That would be the most straightforward definition I could give. So for instance, when we're talking about air in this room where I am right now, there is a certain amount of information required to nail down the precise positions and velocities in the classical language of the particles, or the precise quantum state of the particles using the quantum mechanical language, and that would be the information content of the air inside this room. And when we talk about entropy, entropy arises when we don't look at the detailed microstate of, say, the particles of air in this room, but rather we summarize their state with more coarse macroscopic features like the temperature of the molecules and the pressure and the volume of space that the molecules fill and the number of molecules. Those more macroscopic qualities don't give us the detailed microscopic information. So we often think about entropy as the amount of hidden information, where the hidden information is the information necessary to specify the detailed microstate of, say, the particles of gas in this room. So that's one answer. But in different contexts, the notion of information can take on somewhat different forms. So the answer to the question, Susan, is somewhat context dependent, but that would be an answer that is quite relevant when we're thinking about the world in the language of statistical mechanics, thermodynamics, and using the concept of entropy. Rob B asks, can the universe be cyclic just by the direction of time? I'm not exactly sure what you mean by just by the direction of time, but when people talk about a cyclic universe, it's usually one that in one form or another goes through some sort of origin-like event, a Big Bang-like event, develops, evolves for some period of time, and then somehow finds itself back in a configuration that yields an event analogous to the original creation event, some new kind of Big Bang event. So there is this ekpyrotic scenario that was developed in the context of string theory, where these large membranes, three-dimensional membranes, could float through a higher dimensional space, slam into each other every trillion years or so, and that slamming together would be the Big Bang-like conflagration that would start the cycle anew. There was an older idea going way back to the early days of general relativity, as Richard Tolman was developing these ideas, where the universe would have a Big Bang, it would expand for a while, reach a maximum size, and then come back in on itself, collapse back down, and then the cycle would happen repeatedly. That particular model had problems in dealing with the second law of thermodynamics, because in that case, the buildup of entropy would strongly suggest that the sequence of Big Bangs and big crunches couldn't go on forever. So there'd have to be some initial event, and therefore the cycles couldn't go on forever. But others in the more modern incarnation of these ideas, like Paul Steinhardt, working with people like Neil Turok and others, early days, Bert Overett, also postdoc of mine at Columbia, Justin Curry, they had early models of this. They've developed versions of the cyclic scenario that seemingly can go on forever and still not have an issue with the second law of thermodynamics. Not everybody agrees with that those models actually make sense. You may recall in our conversation with Lenny Susskind, Lenny was definitely, no, it doesn't work. You know, that's like a perpetual motion machine. So I'm not going to get into the fray on those particular arguments. I understand the arguments from both sides, but that is what we would mean by a cyclic universe. All right, we're heading on now to 2 hours now. I'm a little exhausted. You probably are as well. Some interesting questions here. Liam, what is the relation between symmetry breaking and the standard model? Where does it break? So symmetry breaking really should be thought of as symmetry hiding. I'll end on this, I think. So the idea is that if you have certain mathematical equations that enjoy a certain kind of symmetry, when you change around the symbols according to some rule of transformation, the resulting equations are unchanged. That's what we mean by the standard model have certain symmetries. It has a symmetry that has a name, SU3 cross SU2 cross U1. These are non-abelian and abelian gauge symmetries that the equations of the standard model enjoy. When we say that the symmetry is broken, we don't mean that the equations somehow are changed. Rather, we envision applying those equations in an environment, in a world, and that world environment has qualities that do not respect the symmetry transformation. And that's where the symmetry is broken. It's an environmental fact, an environmental quality that doesn't respect the symmetry that the fundamental equations do. So the equations have the symmetry, but the symmetry becomes hidden by the qualities of the environment. For instance, the environment may be threaded by a Higgs field, and that Higgs field may have the property that it doesn't respect certain symmetry transformations, and that's why the symmetry becomes hidden, or in the language of the field, it becomes broken. And that's vital to the standard model of particle physics, the core theory that Frank was talking about. And it's one of the vital ideas in our understanding of the physical universe. All right, I think that's it for us here today. Thanks for tuning in. We will probably have another one of these sessions. We seem to be doing them on a rhythm of every 2 weeks. We do look at your suggestions, keep them coming for people that you would like to hear from. Frank was one of the suggestions, and you see that we now had a conversation with him. There are other interesting folks out there in the world, some Nobel Prize winners, some not Nobel Prize winners, just interesting thinkers across the board. Send in your thoughts of who you'd like us to have that conversation about, and we will join again in roughly 2 weeks. Again, you should sign up for the World Science Festival newsletter so you can be alerted when these sessions happen. You can follow the World Science Festival on the usual social channels, Twitter and Facebook, and you can follow me on Twitter as well. I'm at @bgreene on Twitter. You join in. I announce these sessions there as other tidbits of science, and I'm starting to use Facebook a little bit more. I kind of let it go for a while. We'll see. But I also am @bgreene or Brian Greene at Facebook. Okay. Look forward to seeing you next time.